This is part 3 of chapter 10.1. I'm going to write some formulas, but we developed them in class. So the one thing you should have memorized from the course earlier is that when you have a function y equals f of x that's smooth, then the length of the curve from x equals a to x equals b is the formula that's written here, and we developed that proof for that. The proof for the next one, when the curve is defined parametrically, the length of that curve is from t equals a to t equals b of the square root of dx dt quantity squared plus quantity dy dt squared dt. Now the proof for this was just like the proof for the one we did before. Please consult a peer to look at that proof. So that's the formula. The other formula we're going to look at now is for a curve x equals x of t and y equals y of t. We're going to look at the surface area, and the surface area will equal the integral from a to b of 2 pi radius times the quantity we spoke of before, dx dt squared plus dy dt squared. Again, this was developed in class. Now, if you are revolving about the x-axis, so you take a function or a curve and you revolve it around the x-axis, then this radius here is going to be the value of y of t. And if you take this curve and that we're calling C and you revolve it around the x-axis, then it's 2 pi x of t and times the quantity that we have above. So I just wrote the formulas here in class. We really developed these so that people understood it, but for now I'm going to need you to memorize this, and let's do a couple examples with it. In this example, going back to example 1, we're going to find the length of this curve. So the length of this curve is equal to the integral from t equals -1 to t equals 2 of the square root of the derivative of x with respect to t, which is 2, and then the derivative of y with respect to t, which is 2t, and then that quantity gets squared dt. Simplifying that, we have -1 to 2, which is the square root of 4 plus 4t squared dt. And even though I think you should be able to right now integrate this, it requires a trigonometric substitution, which I'm not going to spend the time doing. So then the answer comes out to be 8 I don't recall this, but 8 maybe 112, something like that, and that was evaluated in a calculator. In example 2, we had a circle. Let's take a look at just one revolution of the circle, 0 to 2 pi. Obviously, the length of that circle will be 2 pi a, the circumference. But let's do it using the integral. So the integral from 0 to 2 pi, square root of the derivative of x with respect to t comes out to be -a sine t, and we're going to square that. And that's the work I also want to see on the exam, is what is the derivative, put it inside the quantity. And then we have a cosine t squared dt. This works out nicely. That's the integral. Then we're going to have inside the radical a squared sine squared t plus a squared cosine squared t. Pardon me, I'm getting very sloppy. So that is going to equal the integral from 0 to 2 pi of, well, factor out a, and we have radical a squared, and then we have the identity again, dt, which is the integral from 0 to 2 pi of simply a dt, which is going to be at from 0 to 2 pi, which equals 2 pi a, the circumference. Final example, number 5 in the notes, wants you to take this parametric equation, this curve defined parametrically, and it wants to find the surface area if this curve is revolved around the x-axis, So the surface area equals the integral from 0 to 2 pi, 2 pi times because it's around the x-axis, we need the value of y, which is 2 plus sine t, radical, and the derivative of x with respect to t, negative sine t, the derivative of, and that's squared, pardon me, and the derivative of y is going to be cosine t squared, and all of this dt. So this radical here, because of identity, equals 1. So we're left with the integral from 0 to 2 pi, 2 pi, 2 plus sine t dt. Work that out, and it comes out nicely. You can do it by hand, 8 pi squared. And lastly, I want to just talk to you about the homework. The homework is on the worksheet attached to the notes packet. There's a great set of problems. Some of the things have you remind you to do integration by parts. It's a nice review to do at this time. But in addition to that, in section 10.1, I think some textbook problems are good. 9, 11, 16, 17, 26, 27, 30, and 42 from the textbook to go along with the worksheet in class. Please remember that most mistakes are made when people are trying to evaluate this. They forget to divide by dx dt.